Okay, we'll probably finish up with this set of notes, uh, or almost finish with it, and then review on Monday and exam on the final on Wednesday. Okay, so alcohols. We've talked about alkenes and alkynes nomenclature, and we talked about the nomenclature for aromatics. And so the next functional group we're going to talk about are these alcohols. So the name is going to change. The suffix will just end in an OL. We'll get rid of the E at the end of whatever it is we're talking about. Like if it was ethane, it becomes ethanol. The OL is letting you know that there's an alcohol there. So I'm still going to be using whatever the most reactive thing as the name. And in this case, all of these are going to be reactive because of the alcohol. So the first one is ethanol, drinking alcohol. It's ethane with an OL, with an OH on it. So that we again drop the E off the ethane name and put OL and say ethanol. It does kind of sound like an AL, all, but it's definitely OL. So the next one, I've got 3 carbons, so a propyl group, and then the central carbon, I've got an alcohol group, and so we're going to call that 2-propanol. That's the IUPAC name. A common name for it is isopropyl alcohol or rubbing alcohol. And so why is this one called isopropyl? It's connected to the middle. So propyl alcohol or 1-propyl alcohol, it would be connected on either end, but this one's connected to the middle, which is actually the way it would prefer to be connected. During the course of creating rubbing alcohol, we were just trying to create propyl alcohol, and then we realized that isopropyl alcohol is made like 95% of the time. And pretty sure we're going to talk about why that's the case a little bit later. I might be wrong, but regardless, the substituted group likes to go to the carbon that's got more carbons on it. That ends up being what the rule is. So if I'm going to react this and my options for the alcohol are on carbon number 2 or carbon number 1, it's going to go to carbon number 2. It wants to be more to the middle than at the end. But for our purposes, this is just 2-propanol. On the next one is 2,4-pentane diol. So this looks a little bit different. I'm keeping the whole name, the pentane name, because it's 5 carbons long. And then I'm going to put DI for 2 and then OL for alcohols. And then the numbers in the front are letting you know that there are indeed 2 alcohols and their positions are in position number 2 and number 4. And then the last one there is just cyclopentanol. You don't need a number because there's only one of them there. If there was any other substitution on it, then I would need to number it. But since it's by itself, it's out. Whatever carbon it's attached to is going to be carbon number 1, so it's not important. Okay, so the ethers are kind of fun to talk about, at least the common names, but we'll talk about the 2. We'll talk about the IUPAC naming and then the common naming for this. So the common naming one, what you do is you identify something as an ether, and you identify it as an ether because it's an oxygen that's sandwiched between 2 carbons, whether it's a long chain or a short chain. Regardless, I've got a carbon and then an oxygen and then a carbon. There aren't any double bonds anywhere. So once you've identified that it's an ether, then you just sort of say what's on one side, and then you say what's on the other side, and then you say ether. So the first one is methyl ethyl ether. Why? Well, it's an ether for sure because it's sandwiched in the middle of some carbons. One side's got 2 carbons, one side's got 1 carbon. So I just say what those side chains are attached to the oxygen. So there's a methyl group and an ethyl group. The next one is butyl ethyl ether. And that's because on one side there's 2 carbons and on the other side there's 4 carbons. The next one is phenyl propyl ether, and that's because on one side there's a benzyl group or a phenyl group, and on the other side there's 3 carbons attached to carbon number 1. If it had been attached to carbon number 2 on the propyl group, then it would have been phenyl isopropyl ether. But really what you do is you just basically cut the molecule in half right through the oxygen, and then count carbons on one side, count carbons on the other side, and then treat them as side chains. They don't need to be numbered because we know, since you said ether, that they're attached to the ether. That's not the IUPAC nomenclature, though. The IUPAC nomenclature is actually harder. Doesn't need to be, and most people don't even use the IUPAC nomenclature. They use the common nomenclature because it's easier. So what you do is you find the longest carbon chain. So the longest carbon chain in this first one is 2 carbons, so it's an ethane. And then it's connected to an oxygen, and then what's on the other side of the oxygen? It's a methyl group. So what you say is meth-oxy-ethane. So the meth-oxy is letting you know that there is an oxygen, and what's attached on the other side is 1 carbon because it's meth. The next one is going to be 1-ethoxybutane. So why do I need a number this time? This thing here is the side chain. And so that side chain is connected to carbon number 1 on this butane group. So it could be connected to carbon number 2. And in that case, it would be 2-ethoxybutane, but it's connected to the first carbon. So that's why we're calling it carbon number 1. And your only options in this would be 1 and 2, because if you did 3, that would turn into 2. And if you did 4, that would turn into 1. You okay with that, Ethan? You got a pensive look on your face.
Just confuse that to 1.
So 4 carbons. I could connect something here, or I could connect something here. So that's why. So in this case, the thing is an ethoxy. It's an oxygen with a 2 carbon side chain on the other side of it. So that's why it's ethoxy. And that thing is connected to the butane on carbon number 1 here, but it could have been connected here. And then it would be 2-ethoxy. So the 2 is just referring to the position on the butane group. And the last one here, you could have named this a couple of different ways. This could be 1-phenyl propane. And so, phenoxypropane. So they're counting this whole thing as a side chain. And they're saying that that is phenoxy, meaning there's an oxygen attached to the main chain and a phenyl group on the other side of it. That's fine. But it's a 3 carbon side chain. So I'm going to say that it's 1-phenoxy because it could be connected to the middle carbon, which would make it 2-phenoxypropane. Is there another name we could have given this? What if we said this was the side chain and the main chain was the benzene? That's it. Propoxybenzene. Yeah. Prop meaning the 3 carbons, oxy meaning the oxygen connecting the 2 pieces to the benzene. That's it. So unless I'm asking you specifically for the common name or the IUPAC name, I don't care which one you use. If it just says name this, then just give me a name that would be. I mean, again, all we're trying to do with the names is to write something down so a person could look at that name and either visualize or just write down what the structure is. Because the thing that's important is the structure, not the name. All right, thiols. So in your polyatomic ion sheets, there was a thiol in there, and what the thiol is an old nomenclature for sulfur, and we've held on to that. So if you see anything in like an ingredients label or something of that nature in MSDS, then that thing has sulfur in it. And so it looks a lot like an alcohol. They're in the same column, the sulfur and the oxygen. So they behave very similarly. Well, what's the difference between the thiols and the alcohols? What?
You said.
Yeah, what's the difference between the oxygens, like, on like a fundamental, like the properties of them? So I've got a thiol here and I've got an alcohol here, like, what's the difference between those two things?
Is it different, like electronegativity wise, or is it like that sulfur can form on bonds? Something weird.
Both of those are fine, but like, one's gonna be really important to you. As humans, what are you really good at?
Things that are rough, so sulfur smell.
The sulfur one's gonna stink. It's gonna stink bad. So even though they're very similar chemically, your nose perceives sulfur much differently than it perceives oxygen, even if it's in an SH versus just sulfur in some other form. So those things stink, like really stink. So all we do is we basically name it like it's an alcohol, except we put thiol instead of all. So that bottom one down there was 1-butane thiol, although we do keep the E for some reason. So you just count up the number of carbons and say the thing's name, and at the end you tack on thiol. So 1-butane thiol. The next one is 3-methyl 1-butane thiol, and it's the thiol gets priority because it's more reactive than the methyl group. And then we've got a 1,3-butane dithiol, carbon number 1 and carbon number 3. That last one is one of the many molecules that a skunk makes. It's also one of the molecules that they throw into natural gas. So why is that added to natural gas? So if there is even the tiniest natural gas leak, somebody leaves the stovetop on your gas oven, you will know basically immediately. It will not be something that you can avoid, like our window being open at night and the fan being on just to cool the room down. I know instantaneously that a skunk has been run over or attacked. Got to close all of the windows immediately because it's that potent. So really we treat them like alcohols that stink. All right, aldehydes. So we've got IUPAC naming for them. We've got common names, and then we've also got a couple of very common names. So this one kind of looks like the alcohol as far as the nomenclature goes. It's an AL instead of an OL, and we really hard sound the A. So the first one is ethanol. That's how I know the difference between ethanol, and that's how I know the difference between an alcohol and an aldehyde. The alcohol is ethanol and the aldehyde is ethanol. So just like you're saying the male name Al, that's how you end all of these. So this is ethanol because it's a carbon doubly bonded to an oxygen. And there's only 2 carbons there. So the double bonded oxygen, that carbonyl group, has got to be on the end for that one. So that one's easy. And we're not going to need any numbers for any of these aldehydes. How come? They have to be on the end because one side of the carbonyl group has to have an H on it. So I've got ethanol, propanol, butanol, octanol. Like, they're pretty boring. You're just counting up the number of carbons there and throwing an AL on the end of it. You're actually just getting rid of the NE and putting on AL. Or getting rid of the E and putting on AL. Okay, so that's it. There isn't really much to the IUPAC name. There are some common names like ethyl aldehyde. So each of these common names, they're just saying the word aldehyde and then telling you how many carbons are there. So ethyl aldehyde, propyl aldehyde, butyl aldehyde, octyl aldehyde. If you go to look up, like you want to buy some butyl aldehyde, you're going to see butanol as a name. You're going to see butyl aldehyde as a name. So you'll see both of them, won't be a big deal. Then we've got a couple of very common names. The first one, I'm sure you've heard that name before, formaldehyde. The middle one is acetaldehyde, because for a long time, two carbons was referred to as ACE. T, so ACE used to be two carbons, so you might see acetaldehyde instead of ethylaldehyde or ethanal written. And then the last one is that benzaldehyde. That was one of those functional group things that we talked about on Monday about the benzene rings. That formaldehyde is just named that because if it's we're gonna see in a little bit that the acid version of it is one carbon, and that comes from ants, and so formic, and so they just took that same name and changed it from formic acid to formaldehyde. So that's where that name came from. They thought it was coming from the same place, didn't matter, but it was one carbon, so they sort of kept that nomenclature going. So I'm sure we've seen formaldehyde. Do you have an IUPAC name for that one and a common name for that one? Can you give me an IUPAC name for that?
For which one?
For formaldehyde? Methanal. Yep, it's one carbon, so meth. So you just say, basically you say methane al, methanal. And then what would the common name for it be? Methylaldehyde. That's it. You're just gonna give me the number of carbons in the side chain format and then just say the name aldehyde.
It feels weird to call that methyl when it's just like.
Yeah. Well, there is one carbon there, right?
Yeah.
Yeah, just like methane. Yep.
It makes sense since that carbon's number one.
But it's weird because we usually don't identify that functional group as the thing, but in this case, we need to because it's the basis for the molecule. Have any of you read anything about formaldehyde being phased out of products? So Hurricane Katrina flooded basically Louisiana and surrounding states, but Louisiana was hit the hardest. And we did a lot of temporary housing stuff. I mean, you shouldn't be living in a city that has a decent portion of its population underneath the water line. Bad idea in an area of hurricanes, but they did it anyway. And so a lot of people were displaced. And so every single mobile home was purchased by FEMA and brought to the area. So many of them got taken off the market that the mobile home companies just started pumping these things out as fast as they possibly could. But there's a 60 or 45 or 60-day curing period for these for like RVs and mobile homes, because they use so many products that have different volatile chemicals and adhesives. So like at your house, if you've got carpet, like this carpet in here, actually I don't know about this carpet, I won't say, but the carpet in your house is not glued to the subflooring, but in a mobile home, it is glued to the subflooring. So that glue is volatile. That like, oh, it's a new car smell. Oh, that's just a bunch of volatile organics that are irritating your lungs and esophagus. Like you shouldn't be breathing that, but people like that smell for mostly because it's a new car. Though you shouldn't be breathing those things. Those things should be vented out of whatever it is you're going to be inside before you get to it. Like they should build a new car, roll the windows down and put a box fan in it and leave it there for a month before it actually gets sold, but they don't do that. Same thing with these houses, but because they were in such need in the area, they were slapping these things together and then just putting them on trucks and sending them to Louisiana, I guess Mississippi, some parts of Texas, regardless, all those places that got hit. And then people were getting these things and they were, they were brand spanking new, like it was built last week, and they go in and then they find out that like they wake up teary-eyed, esophageal issues, lungs, people who had gone in and had emphysema or issues. One of them caught on fire when somebody was trying to light a match. That's because there were so many volatile organics inside the space, this tight space, from all of the different adhesives that they used, that the space was filled with mostly formaldehyde and a bunch of other stuff. And to that point, formaldehyde had basically gotten a pass as it wasn't a problem. And then it turned out it was a huge problem. So the wood that's used for interior building in houses now either has to be ultra low formaldehyde or aldehyde free. And that was one of the reasons that lumber costs went up, not lumber per se, but more like the name of those boards is escaping me, but the 4x, say again?
Plywood?
Yeah, like plywood, like 4x8 strip things of plywood. Those prices skyrocketed because they had to come up with an entirely new adhesive system to get those together. Because really, what they're either pieces of thin board that are stuck together, or they're literally just like wood chips that have a glue that has a formaldehyde base that leaves after a certain period of time, but it takes a while to vent. Same situation with like not necessarily IKEA, but IKEA style products. So you can go to Freddy's and you can buy like an entertainment center that's built in the same fashion that IKEA is. Like you have to put it all together yourself, and it has that press board stuff that you can't screw into because it's like drywall. That thing that holds that together is formaldehyde, formaldehyde based adhesive, and so we had to come up with a bunch of different adhesives to do that. These types of countertops, they were all glued down with a formaldehyde based adhesive. And so all of that stuff had to disappear. And it's taking a while for us to get through that process, but it turns out that it messes with the body in ways that we weren't expecting. And we hadn't noticed it because most people followed the guidelines that you wait X number of days before you move in or sell those things. Still venting. Yeah. Because even though the most of it, like the first 45 to 60 days, 90% of it gets vented off. The issue is it's still venting that stuff. And so even though you've got most of it gone, if you're just like laying in a bed and the bed frame is made out of a formaldehyde based adhesive, then you're constantly being exposed to small doses of formaldehyde, and you'll be doing that for the next 20 years as you sleep on that mattress on that bed frame. And that has caused problems. So they've realized the long-term effects. Nobody was bothering to look at it because it didn't seem like it was problematic. It was more like of a 5 years down the line, things would go bad, but they weren't linking these things up. But when these people were like adversely affected acutely, like in the first day or the first week, they were, well, maybe we should look more at the chemistry for the formaldehyde. Maybe it's doing things that we weren't expecting it to do, and they did. And they're like, oh crap, this should not be for human consumption, breathing wise. So it's disappearing off of most things. When you go down to Tumalum or to Home Depot, you will see things stamped with formaldehyde free or ultra low formaldehyde, or doesn't require formaldehyde regulation. And that's telling you that board right there was made for an exterior use that people should not be inside of. So it will be the board on the outside of the house. So there'll be like the plywood board, then insulation, and then sheetrock. So that's okay, but it can't be on the other side of that. It can't be on the house side, garage side kind of situation. We had a bunch of that stuff left over after our house got built, and that's what I used in the garage to like board it out. And so I just opened up the doors and left it open for a month, and it was good with a couple of box fans. Okay, ketone. So ketones and aldehydes are kind of look the same. The main difference between them is the aldehyde has to be on the end and the ketone can't be on the end. So the smallest possible ketone is propanone. it would have to at least be 3 carbons long because there's a carbonyl carbon and there have to be carbons on both sides of the carbonyl carbon. So the smallest ketone possible is propanone, and we'll talk about its IUPAC name, its common name, and it's very common. So it's called propanone because the ketones end in an ONE. So basically, just you slide in an ON in between the N and E, the longest continuous carbon strand. So there's 3 here, there's 4 there, there's 5 there. So the second one there is butanone. And again, I don't give a number for the first one or the second one because there aren't any options. For the first one, it can only be on the middle one. For the second one, it can only be on carbon number 2 or 3, which would be carbon number 2 again. Can't be on carbon number 1 or it's not a ketone. The once I get to 5 carbons, then you have a possibility of it being on carbon number 2 or carbon number 3. So then I'm going to have to identify where it is on the chain. So this is 3-pentanone, and the only other option would be 2-pentanone. And then cyclohexanone, that's just a cyclic hexane that's got a double bonded carbon on it to an oxygen, and so that makes it a ketone. And I don't need to number it because it's a circle. So the common names for this, it sort of goes just like the ethers. I just say what's on each side and then say ketone. So dimethyl ether or dimethyl ketone or methyl ketone, one of those names. I've got the ketone, the C double bond O, and on each side of it, I've got methyl groups. The next one is methyl ethyl ketone. And since these are common names, they don't need to follow the IUPAC nomenclature. So it doesn't need to be ethyl methyl ketone. So if you go to the hardware store, you're going to see this as a solvent and it'll just be called MEK for methyl ethyl ketone. Super volatile. You wouldn't want to breathe it for too long, but regardless, it's a really good nonpolar solvent. Then I've got methyl phenyl ketone. So a methyl group on one side, a phenyl group on the other side. And then there's no common name for that last one, that cyclohexanone. And then for the ones with very common names, I just have the acetone and the MEK. So I just talked about the MEK. And so I'm sure you've heard the term acetone before. And so that ACET thing was 2 carbons. So what this was a ketone with 2 extra carbons on, so 1 on each side. So that's where the name came from. And it's stuck around in the same way that water has stuck around as a name and ammonia has stuck around for a name, just because it's been around for a very long time. So where do you get acetone? Where do you come in contact with that? Yeah, it's a paint thinner. Anything else?
We use it to rub down oils off the middle.
You can. It's a good solvent. We need Veronica. Can you answer that for us? Can you answer where you would find ketones for these males in this room? Nail polish remover. Yeah, it's nail polish remover. That and nail polish remover is actually the best thing to get rid of Sharpie. So if somebody has written on something with a Sharpie, it will disappear instantaneously by sprinkling a little bit of acetone on, just like gone, like chalk on a chalkboard. This dry erase markers, they just disappear. We had I think he was a sophomore. He was working for the chemistry lab and he came in and he was labeling bottles with a Sharpie, like water, deionized water, ethanol, acetone. And we're like, well, that's not going to work. And he's like, why? And we just like squeezed it and let it run down on itself. And it just washed the Sharpie away immediately. It's like, okay. So super good nonpolar solvent. If you've got like a gunky sticker of some kind, a bumper sticker, a window sticker, and you're trying to get it off, just grab some fingernail polish remover and it will take it off immediately. All right, next one, carboxylic acids. So the carboxylic acids are acids, and they're acids because there's a C double bond O, OH. That OH group was an alcohol, but if it's attached to a C double bond O, it no longer behaves like an alcohol. It behaves like a carboxylic acid. And we had this little discussion before about this being electronegative, and the electrons here get dragged, and the electrons here get dragged, and the electrons here get dragged. And so you end up having a positive charge, partial positive on that H. So that's why it's allowing the H to get plucked off. But the nomenclature is you basically just say however long it is, and then oic acid. So this has to be terminal because it ends in an H. So I've got ethanoic acid, propanoic acid, and in this case, dipropanoic acid for that last one there. Or sorry, propane dioic acid. And then the common names for the first and last one, acetic acid. So ethanoic acid is acetic acid, the acid that you find in vinegar and ketchup and mustard and many different products. And then malonic acid. Has anybody used malonic acid? Anybody taking care of a hot tub or a swimming pool? Probably was just named as like shock or pH treatment or something like that. But malonic acid will be in there, and it's nice because it's got double the acid ability, one on each side. It's also possibly one of the things that makes Sour Patch stuff sour. There are many different things that you could use to give it that sourness, and malonic is one of those things.
We use it in foods, studies and food.
But also foods.
Yeah, but I mean,
Well, I mean, if they can be in your body, it can be in the skin.
Yeah.
all right, ester nomenclature. So the way we're going to name the ester is based off of how the esters are made. And so you make an ester by reacting a carboxylic acid with an alcohol, and you end up making a water molecule and an ester. So let's do an easy one here. So I've got CH3, CH2, C double bond O, OH, and I've got ethanol. All right. So what ends up happening is this H and this OH leave as a water molecule. So this carbon here needs a bond, and this oxygen here needs a bond. So we end up with CH3, CH2, C double bond O, O, CH2, CH3. So this is this. And all of this is this part right here. So it's a dehydration reaction, water disappearing, and we're left with this ester. So what we do is we name it for the two parts that it used to be. And so we're going to name it for the alcohol first, and then we're going to name it for the carboxylic acid it was. So when you look at this ester and you want to name it, what you do is say, okay, so this part right here used to be an acid. So this is going to be the end name. This part right here used to be an alcohol. And so I'll name that first. So this guy is methyl ethanoate. So remember when we were doing acid nomenclature and polyatomic ion nomenclature, like phosphoric acid came from phosphate. So that's why we get this 8 thing here. So ethanoate used to be the acid ethanoic acid. It lost its H, and so it became a polyatomic ion, basically. So that's where the 8 came from. And then now it's attached to this, what used to be methanol, and so it's methyl ethanoate. So this next one, this is a 3-carbon piece that used to be propanoic acid. So that became propanoate. And this used to be ethanol. And so that's why the beginning part here is just ethyl. So when I'm looking at these things, you find the oxygen that's sandwiched between the carbons and you cut it in half. And then you name this thing as a side chain, and then you name this thing as something that used to be an acid with the suffix ate. So this is phenyl ethanoate. It's just 2 carbons. And this is the ripening process that happens in fruit. There'll be a carboxylic acid and there'll be an alcohol, and those 2 things will come together and create an ester, and then the fruit, that's the fruit ripening. And that ester smell that is created is volatile, so it comes out, and then that causes all of the surrounding fruit to start its esterification process. And so like one banana that, like if you've got a bunch of green bananas and you've got an old banana from an old bunch and it's brown, just set it on top of it, or better yet, put them all in a bag together, and those green bananas will esterify and ripen much more quickly than they will on their own. All right, so amine nomenclature. There's a couple of ways to do it. There's a IUPAC version, and then there's something called the chemical abstract form. So chem abstract or CA format is comes from a journal of sorts that attempts to help name things, and so they've got a format of their own. So first off, we have different versions of the amine and the amide. There's a primary amide, primary amine, a secondary amine, and a tertiary amine. So what those things we're referring to is the number of carbons that they're connected to. So the primary amine is connected to 1 carbon, the secondary amine is connected to 2 carbons, and the tertiary amine is connected to 3 carbons. And that one on the end there is an amide, and it's a primary amide because it's connected to just 1 other carbon. So we can name these things as amines. So for this first one here, it's 1 carbon. So I'm going to have to identify that there's 1 carbon there. And there's also an N there, and the N is connected to a C. We need to be super clear that the N's in these first 3 examples are amines, because the C that they are connected to is not a carbonyl carbon. It is not a C double bond O. It's just a straight up C with other C's and H's connected to it. So this first one is just methamine. So the methamine is telling you that there's 1 carbon, and then there's also an amine group. And so going from the name to the structure, you should be seeing, okay, so it's meth, so I've got 1 carbon, and then I've got an N. So you just connect a C and an N to each other, and then fill out H's until the C has 4 bonds and the N has 3 bonds. So the next one, the nitrogen is connected to 2 carbons. So I'm going to have to identify that in some way. And so the way it works is the first thing that I do is I take this part, I ignore that side chain thing for a sec. And I'm like, okay, so what's this thing right here? Well, that's a 2 carbon chain with a nitrogen on it, and there's no carbonyl carbons. So this is ethamine. So eth meaning 2 carbons, and then amine meaning it's a nitrogen connected to it. And then I write what the side chain thing is connected to the nitrogen by writing N-methyl. So why do I do that? I need the methyl part to let you know that there's 1 carbon, and I need the N here letting you know where it's connected on this molecule. And in this case, it's connected to the N and not to some other place on the chain. Let me let's pull up this. Ooh, nope, not doing that. So when I look at this molecule, I'm like, okay, so the longest carbon chain is 4. So that's a bute. There's a nitrogen here and no carbonyl nitrogens. So I'm going to call that butamine. All right. So when I've named butamine, I have counted all of this. All of this is taken care of so far. So now what I've got is a side chain and a side chain. Okay. So how do I identify that these side chains exist? Well, one of the side chains is directly connected to the nitrogen. So I'm going to say N methyl. And so now this one's taken care of. And then I also have to say 2 methyl, because this methyl is on the main chain in position number 2. You okay with that?
Would it from the nitrogen or the carbon on the end there? Would it be?
From the carbon. So if it's connected to the main chain, I use the normal nomenclature with numbers, but if it's an extra side chainy thing connected to the nitrogen, I just say N. So I do have the possibility, since the nitrogen can make 3 bonds, that it could be NN. So this nitrogen has no hydrogens attached to it at all. There's a methyl group and a methyl group, and the longest chain is this ethyl group. So it's ethamine. So eth or ethane amine, great. And then it's 2 methyl groups attached to the nitrogen. So I say dimethyl. And then I'm letting the person know that those methyl groups are attached to the nitrogen. So it's N, N. Okay with that?
Would you ever see like common and dimethyl, or is that both ends of ends?
They don't mix. Yeah. The IUPAC format is a little bit different. What it does is it treats the amine group as a side chain that's called amino. So this first one up here, that's a methane molecule with an amine attached to it. So I'm going to say amino methane. This nomenclature is used much less. The next one is ethane, and there's a nitrogen attached to it. So it's amino ethane. The next one, this kind of shows why it can be a good nomenclature, because this is really easy to see. This is a butane molecule. The amino group could be attached to carbon number 1 or carbon number 2. So it's attached to number 2, so it's easy to just say 2-amino butane. That's letting you know that the NH2 is just attached to carbon number 2. We do have to use that N nomenclature when we're talking about if it's got another carbon connected to the nitrogen. So in this case, the longest carbon chain is ethane. So I just say ethane. There's a nitrogen attached to it. So that's where the amino comes from. And then there's also this extra carbon on the nitrogen. So it's N-methyl amino ethane. And then the last one we're going to talk about is the amide. And the amide and the amine are pretty similar to each other as far as the nomenclature goes. Instead of saying an amide, I say, instead of saying amine, I say amide. And so ethane amide, propane amide, N-methyl propane amide. And so the reason this one's 2 carbons long, so that's why it's ethane amide. This one's 3 carbons long, so that's why it's propane amide. This one's 3 carbons long, so that's why it's propane amide. But the nitrogen also has this extra methyl group on it, so that's why it's N-methyl propanamide. I mean, the names are pretty straightforward, but you can see why that first week of organic chemistry, people start dropping out. Like, I don't want to have to memorize all this stuff. So that's what happens. And everybody I've ever known, the professor says the same thing the first 5 minutes of class. I expect 20% of you to be gone by next Monday. My class had 50% attrition by the end of it. And at that time, if you wanted to be a nurse, you had to take general chemistry for chemistry majors and organic chemistry and biochemistry. So my class, I had a guy who was pre-med and a woman who was pre-nursing sitting next to me, and we like powered through the whole thing. But that's usually what happens. You get, and he said that too. Like if you're in here pre-med and this class is hard to you, just switch majors.
It's like this nomenclature, but it just gets absurd. You start thinking more.
You just start basically, I mean, I showed you the names of those molecules, right? That were like sentences long,
Yeah.
several lines long. And so they just keep getting longer and longer. But again, coming up with a name can always be a little bit confusing. But if I'm, even with those super long names, I look at it and I'm like, all right, well, this means there's 17 carbons. This means on carbon number 6, this thing's attached to it. And this means that on carbon number 3, this thing, I mean, they're very German in their like utilitarianness. But they can just kind of be overwhelming. Like listening to somebody speak Shakespeare, and you're like, nobody should talk like that. I understand if I break down each sentence, but I shouldn't have to bust the sentence down to understand what you mean. Like reading the Constitution. Like, why did you have to write it? Why did we need a Supreme Court to interpret what you meant? Why didn't you just say what you mean? All right. So a whole bunch of nomenclature stuff. We're going to talk about some things that I had skipped or I said that we'll talk about later on, which is geometric and stereoisomers. These things don't really apply to inorganic chemistry. They're really organic chemistry only. And so we already talked about isomers. And so the easiest isomer to talk about is something like butane and 2-methylpropane. We both have the same chemical formula, but they have different structures. So one's 4 carbons in a row, one's 3 carbons in a row with a 4th carbon coming off the middle. So these are definitely different molecules. They're connected differently. Like if I'm going to build one, I'd have to pull the thing apart and reattach something like that. So now we're going to talk about when that doesn't happen. So the geometric isomer is an isomer that happens based off of its position in a molecule. We never have geometric isomers with single bonds. They only occur, or triple bonds, they only occur with double bonds. That's it. The only time it matters is in double bonds. So the whole reason is because around these sigma bonds, there's complete and utter free rotation. So nothing is in a fixed position. They can just rotate as they want to around. So I had on the lab, you guys were supposed to draw something that looks like this because you're supposed to look at it. What will it look like if I was looking at it from the end? And so it does this. Maybe it wasn't in the lab. Maybe it was one of the worksheets. But regardless, it does this because these H's have hydrogen or electrons around them. And so these 3 that are in the back are further away from the 3 that are in the front if they're offset. Over here, these hydrogens have gotten closer to each other. And so their electrons would sort of push each other away as they rotate around. So it'd be like a. So let's look at this structure. So the first one is 1,2 difluoroethane, and the next one is 1,1 difluoroethane. There isn't an issue with the second one, but there is an issue with the first one. So what kind of issue could we have with that first structure? Yeah, the 2 fluorines are both on top. Well, what if one of the fluorines was on top and one of the fluorines was on the bottom on the other one? Does that matter?
It's rigid, so it does.
It's rigid, so it does. So this is why it doesn't matter in single bonds, but it does matter in double bonds. Is it a big deal? Yeah, it's a huge deal. One of them allows you to build cells in your body, and the other one doesn't. Like literally, we're talking about cell walls being able to be built or not be built based off of, are they next to each other or are the functional groups opposite of each other? And so does anybody remember what that was called when they were next to each other? I mean, we briefly talked about it. It was cis, same side, cis. And if they're on the opposite side of each other, trans. So if that fluorine is here and the H is here, this would be trans 1,2-difluoroethene. So when I see this name 1,2-difluoroethene, I say to myself, which one is it? Is it the cis version or the trans version? Because now there's another thing that I have to keep in mind because there's no free rotation around that double bond. So this one matters, and these two don't matter because of the rotation. So which one of these two things do you think is more reactive? The one with them on the same side or opposites? There's a boatload of negativity on that. If I'm making this, the chances of me making the cis version is small by comparison to the trans version. Why? No, it's not about reacting. Fluorines have lots of electrons around the outside of them, right? So I'm not going to have one that, if they were to go to put on the same side, the other one just get pushed to the opposite side. This is one of the reasons that synthetic organic chemistry can be expensive. So let's say I'm trying to make the first one, but when I put this stuff in a pot, this would be ethene and fluorine gas. 90% of what I make is the trans version, but I'm trying to make the cis version. So then only 10% of what I made is usable. So I basically have to get rid of 90% of my product because I only want this 10%. Does that make sense? And that can happen if the molecule needs to be cis. If it happens that you need the trans version, that's great. Like when you buy rubbing alcohol, it's almost all isopropyl alcohol. There is propyl alcohol in there, like 5% of it. Nobody cares because they both kill stuff, but nobody cared enough to make it just propanol, one propanol. It doesn't matter. They both do the same job, so just put them both in the same container. Okay, so it starts to matter more and more based off of the size of the molecule. So why does it matter more and more? Well, remember when we're drawing the up, down, up, down, up, down? This is up, down, up, down, up. This is still kind of an up, downness as I go through this. But this one doesn't do that. This is up, down, up, down, up, down, 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 down. So there's like a break in the form of the molecule itself. It doesn't sort of like keep going in this zigzaggy yet straight line. It causes a bend in the molecule. We've seen it. Does anybody remember where we saw it? It was last quarter. There you go. It was about the fats. Let me pull up those notes. We had a discussion about, wait, is it not this set? Nope, not this set. This one? No. Is it in liquids and solids? I think it's in liquids and solids. There we go. So here's stearic acid and palmitic acid, and then stearic acid and oleic acid. So the oleic acid has a double bond in it. We can see it there. And so the result of that is that it turns. And that's important. So which one of those things like is problematic, the cis fat or the trans fat? Trans fats are banned. You can't sell anything with trans fats in it. And we had this discussion before. Does anybody remember what the real issue was? It can't, the trans fats can't be used by your body other than fat. And they form the low and very low density fats. So the things that cause artery blockages, that happens because of the trans fats, not these fats. The double bonded cis fats are what we use to make cell walls. So they have a functionality to them. The trans fats, we can't do anything with them. So we had a spike in heart disease for several reasons, but one of the main reasons was margarine. So why is margarine supposed to be a good thing or a healthy thing? It's plant-based. Okay, that's fine. Nightshade is a plant. That does not mean I'm going to eat it. All right. That whole, well, it's natural. Cyanide is natural. Cyanide is organic. I'm not going to eat it. So you can't say that. So the issue was we were creating like this kind of thing comes out of plants. But what tastes better? Bacon grease or corn oil? Bacon grease, obviously. They'd make French fries out of bacon grease if they could afford to do it, but we simply don't have enough money. We don't want to spend $12 on a small fry is really what it works out to be. So how do I make this fat taste like bacon fat? I got to get rid of this double bond. Well, how can I get rid of this double bond? Well, what if I took hydrogen gas and I bubbled it into a container of this? And that way, since these double bonds are reactive, I got the H's here and then made this stearic acid, made it a straight chain, no double bonds. Like, oh yeah, that's going to do it. So, well, it turns out that reaction is kind of slow. So how do I improve it? Well, let's put a catalyst in there. So the catalyst is nickel. It's literally a vat of corn oil with a radiator looking thing of nickel. So the hydrogen and the oil go in between the little pockets on this nickel radiator looking thing. And remember what metals do with gases? We had that discussion about catalytic converters. The gases adhere to the surface of metals. So they adhere, the hydrogen adheres to the surface, then its orientation is more easily, because I've gone from 3D to 2D. And so I've got 1,000 times more likely that it's going to run into the right spot as far as the molecular collision theory goes. So that works. The problem is that nickel also takes this molecule and moves the H to the other side and turns it into a trans fat. So there was no trans fat when it went in. It came because plants don't make the trans fat. It goes into the vat with the nickel and the hydrogen. Most of it gets turned into stearic acid, fat, the fat that would come from beef. So you wouldn't be able to tell the difference between the two. The problem is there's like 10 or 15% of it that didn't convert to stearic acid because they just didn't cook it long enough. Cook it's probably not a bad term. Let it react long enough. And so then you've got this oil that's floating around in there that's a trans fat. We're like, whatever. It's been in there long enough. It's sort of solid. It's sort of like butter, but it's not, right? I mean, if you've got butter and you've got margarine, I mean, the margarine could be in the refrigerator. You pull that thing out, you can still spread that across toast. Butter pulled out of the fridge, I mean, you're going to tear the toast up. Why? Because there aren't any of these double bonds. It's all single bond stuff. And so they lay it on top of each other easily. And so they have a lot of intermolecular forces with each other. So what they ended up doing when they made margarine is they introduced trans fats to people. What did it do to us? It killed us in our 50s and 60s, sometimes 40s, because those trans fats floated around, caught on to all the scar tissue from birth. So have you all seen like a woman with scar tissues because of giving birth around the belly area? Or like a guy who lifted too fast and he's got scar tissues around his biceps or his pecs? That kind of thing happened to blood vessels when we grew. So as we grew, those blood vessels stretched and they actually were traumatized and have these scar tissue spots on them. So the interior of those epithelial cells isn't all nice and smooth. Some of that is scarred. And so these fats that don't want to be in a liquid environment, which your blood is, grab hold of these scar tissue areas and hold on to it. Okay, well, you go 50 years and they just keep holding on and keep holding on. Where does all of the blood go every single time, all the time? Where is it always going to be found?
No.
Nope. And the heart has to be, right? So the heart does two things. It's pumping all of that, but it itself needs blood. So it's giving itself blood and it's pumping the blood for the rest of the body. So all of the blood makes it through the heart, has to. So all of the fat makes it through the heart, including the vessel that feeds the heart its blood. So that vessel itself, it will have scar tissue on it because the heart grew very quickly. And so those blood vessels build up those very low density lipoproteins, like the trans fats that we made. And that's where that comes from. That's where the increase in cardiovascular disease comes from. You can see like, here's the timeline, and here's margarine is introduced, and here's heart disease. Like they directly correlate. But for 100 freaking years, Harvard Nutrition told us that margarine was better than bacon. 100 years. And people still believe this, that margarine is better for you because it comes from a plant. Now, that margarine that we have now is better than the margarine that we used to have. There aren't any trans fats in it. I say aren't any. There still are some in there, but the amount is so low that the FDA doesn't consider it a problem, which I still think is BS. Like any amount of poison is poison. So yeah, no, don't eat margarine. Just don't do it. Butter's better. So the cis and trans part of molecules 100% matters. The chemistry can be completely different simply by making a molecule go from being trans to cis or vice versa. So when we're looking at this, what you need to do is just simply be able to identify functional groups that are kind of the same on each side. And then are they on the same side of the molecule or on opposite sides of the molecule? It can get it's a little bit harder. If I were to draw this structure right here, just as CHs, it might be difficult for you to see. But really, the easiest thing to do in this case would just be, well, where are the hydrogens relative to each other? Same side, opposite side.
Do most double bond molecules have a cis and trans version, or is it only like some?
Any double bond, well, no, it would have to. Okay, so like this one right here, no cis or trans, right? So to be cis or trans, both of the carbons can't have the same thing on one side. Does that make sense? So I don't care like how long this chain is, how long this chain is. If these two things are the same, then if I flip them, then nothing's different. So both carbons have to have different things on them for you to have the possibility of cis or trans. If all four positions, so when we think about the double bond, I think about double bond, carbon, and then something, 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 something. So if each of these things are different and each of these things are different, then I can have cis or trans. But if I don't have that situation, then it doesn't work. There isn't anything new when I swap their positions. Okay, so the cis or trans thing is important, and then this other thing, next thing we're going to talk about is called stereoisomers. So let's. So build a methane molecule that has 4 different things attached to it. Hydrogen and chlorine and bromine and fluorine.
Random stuff.
Yep. 4 different random thingy bombs. Really go on. Going with the halogens and hydrogen. So green, orange, and purple for chlorine, bromine, and iodine. Bromine kind of looks a little bit orange. Chlorine can turn things green. And then iodine is definitely purple. Yeah, that's weird.
So here's Ben's molecule, here's my molecule. I'm gonna point, I'm gonna put the iodine at you and put the hydrogen on top. Yeah. Are those the same thing?
Yes.
No, they're not.
The order. here?
Oh, it's because the, pointers pointing at each other, it needs to be on the other side.
They're mirror images of each other. I can't superimpose these molecules on top of each other, right? Okay with that? The only time the stereochemistry can happen is with carbon with 4 different things on it. But don't get fooled. It could be like a CH2 and a CH3 and a CH9 and an H. If it's carbons around it, you have to keep going a little bit further to see if the carbons are chains that are different from the other things on it. So is this important? Yeah. That means that carbons that have 4 things on them have a handedness to them. There's like a right-hand version and a left-hand version. Your hands are not the same thing. You can't put a left-handed baseball glove on your right hand. It does not work. So that mirror imageness is important because the chemistry can change. And it's hard to see that because if I'm looking at this molecule that I built, what does this carbon have attached to it? An iodine, a chlorine, a bromine, and a hydrogen. Well, what do those have on it? Exactly the same thing. So they must be exactly the same thing, but they're not. So why is that important? Well, we're talking about organic chemistry. And organic chemistry usually combines with biochemistry. So if this is a molecule inside the body, this thing might not fit into an enzyme. Only its mirror image might fit into the enzyme. Are we okay with that? The mirror image might be benign, or it might be fully problematic. Images. That works. Open as a new tab. First molecule that we talked about in this class was glucose. The one on the left is the one that your body uses, beta D glucose. The one on the right is beta L glucose. Your body cannot use that at all. What's wrong with it?
Which is the one that is bad?
The one on the right. Your answer is because they're not the same. That's it. There isn't anything else to it. The thing on the left fits into things. The thing on the right will not fit into things because it's got stuff pointed off in different directions. Same situation with these molecules. And the stereochemistry, the other term for it is chiral. A carbon that has 4 different things attached to it is called a chiral carbon. So there are several chiral carbons on glucose, on this 6 carbon chain. Let's pull up another one of these guys. Have we seen these names before? Obviously, we've seen one of them. These are all isomers of each other. They're all hexoses, right? They're all 6 carbon sugars. And we can't use a damn one of them. There are these 8. Then there are 8 more that are the D versions, and we can use one of those versions. And the 2 of those versions we can convert into the other one. So we can take galactose and turn it into glucose. And we can take, well, can't take any of these other ones. Sorry, there's only one. We just take galactose and can turn that into glucose. So these other ones don't work, but they could exist. They're all versions of this. They're all isometric versions, but nature doesn't make these things because they make them with a particular protein that spits out a particular orientation for all of these molecules. So we don't really need to worry about it. So where do we need to worry about these chiral molecules? People making chiral molecules. That's it. So we come up with a drug that's got a chiral compound in it, chiral carbon in it, and we need to make sure it's not dangerous because that hasn't always been the case. So again, this seems like not a big deal, but it turns out to be a huge deal. So as far as the nomenclature goes, you might see L or D as options. You might see S or R as the two options, or you might see plus or minus as the options. All right. So I'm going to use L and D. I'm just saying, if you're looking in the book, you might see these other two as well. So there's a really weird property of chiral molecules. So if I were to have a solution of this, just this right here, and it was dissolved in something or it was in a liquid form, it actually turns plane polarized light. So let's start off with that. Do we know what plane polarized light means? About just polarizing light?
It gives things purple or nope. That's good. That's like,
Is that like what polarized in that pair?
well. That's invisible, but I don't know. This is a polarizing device. It's not a very good one, but it's kind of good. So is all the light coming through here? No. I mean, there's gaps in it. It's not all coming through. Some of it's getting blocked. What if they were closer together? What if they were layered by microns? So if we remember, light does this. Okay. So the light itself does this up and down thing. So if I try to send this through that, it's going to get blocked. But if I take this thing and I rotate it 90 degrees, then it's going to slide right through. You okay with that? So polarizing sunglasses block light that isn't coming through at the right angle. So I've got 360 degrees of angle, half of that because it can be this way or it could be this way, it doesn't matter. So those glasses can block any of those 180, depending on how close those things are together. Maybe number 180 and 179 and number 1 can all make it through, but everybody else gets blocked. Do you guys know how to check to see if a set of polarizing lenses are actually polarizing lenses?
I used to know.
Take two of the glasses and you rotate them. Once, if I have this Venetian blind and then another one that was vertical, how much light would come through? None. It would all be blocked. So if you take, if these are supposed to both be polarized sunglasses, you just take them and rotate them over the top of each other. At some point, you're going to get them 90 degrees to each other and it'll just go black. So if you're like a cheesy beachside, I need some sunglasses stand, just do that real quick. And it'll tell you if they're actually polarized or not. So polarizing glasses are good to drive with because the sun is coming here, but it's also reflecting off of the ground and other objects. So basically only the light that's coming through at this orientation gets through to your eyes. All the light that's coming through at any other orientation gets blocked by the polarizing nature of the glasses itself. So the reason we're talking about that is because a weird thing happens with these molecules that are chiral. If I take a chiral substance, a pure chiral substance, and I send plain polarized light through it, the light, as it's passing through the solution, will turn. It's crazy. So you can check this by like literally putting like a piece of transparency paper with like a protractor image on it, and then putting a solution over the top of it. And it will cause the protractor to turn the image that you're seeing being projected. And then you can just like measure the degree it got turned. That is a way to determine what substance you're looking at. How much does it shift plane polarized light? And that's where the plus and minus comes from. Does it shift it this direction or does it shift this direction? One of them shifts it 7 degrees this way then the L version shifts at 7 degrees the other direction. But if you mix them together, they keep getting shifted back and forth where it just goes straight on through. So if we got a solution with D glucose and L glucose in it, there's no shifting that occurs at all. But if it's just D glucose, it shifts that plane polarized light spectrum.
Okay, so anybody heard of this? It's pronounced thalidomide. No. It was a biologically active compound, like your papers. And what somebody had found out was that it can basically stop morning sickness. And if you've never been around somebody undergoing morning sickness, it can be pretty awful for obviously reasons that they don't feel well, but not being able to keep food down because they're vomiting, it could actually become problematic for the mother and the child. So any way that we could stop morning sickness, that'd be fantastic. Europe approved thalidomide. The FDA hadn't gone through its process of drug approval. And we never made it through that process because we had this weird situation in Europe where these babies were being born like armless, legless, missing their arm from the elbow down, missing like the nose isn't there, ears are gone, but mostly it was about limbs. And they tracked it back to thalidomide. So what it turned out was one of the versions of the thalidomide did exactly what it was supposed to do. The other version of the thalidomide caused birth defects, massive birth defects. So now if you're a drug company, one of the very first things that your goal number one is let's not make a chiral compound. Let's make no chiral molecules in this thing that we are making. Why? Say again? They could behave differently, but what are all the drug regulation organizations going to make you do? Two things. No? When you make it, what you make is both of them, and that's called the racemic mixture. And they want you to pull the two pieces apart. They're called enantiomers. And so they'll want one solution of L enantiomer and one solution of D enantiomer. So first off, you got to separate them, which can be a major pain in the butt because they're basically the same thing with one carbon, maybe just one carbon, having this chiral nature to it. And then you have to do 2 trials. So drug trials are expensive and time consuming. And so I have to do the L trial and I have to do the D trial. So that can be super problematic. We have actually found out that the thalidomide itself works really well as a mood regulator. So people were like problematic being on lithium, other things. And so the thalidomide can be more mild side effects, but only men can take it. Why? Because the drug companies are terrified that if any woman were to accidentally get pregnant when they said they weren't going to, that they have a deformed baby, that they would just be bankrupt because of it. So it's not allowed to be given to women, which is kind of BS, but regardless, not a thing. So every single time that someone's like, can we rush this through the FDA points at thalidomide and says, no. We have broken that though recently. When did we break that? Twice in the last 25 years, we've broken that FDA rule. Penicillin is way old. What was the other thing you said? COVID vaccine for sure. Obviously, we had that thing made in 9 months. So that broke it. And the other one was AZT for AIDS. So why did it matter? Well, because those people were dying. They're like, yeah, we'll take the racemic mixture. We don't give a shit because I'm going to be dead in a month anyway. So why don't you give me something that can prolong my life or maybe even save me? So that a couple of ways. I mean, there have been a couple of other drugs for very rare diseases, that kind of thing has happened for the same situation where the person, usually it's almost always a kid, is going to die without this thing that they've developed. And sometimes it works and most of the time it doesn't work because it, you know, didn't go through proper testing. Let's see. So like on this one here, it's kind of hard to tell because this is a carbon. There's a hydrogen here, but there's a carbon there, a carbon there, and a carbon there. So I see 3 carbons around it. So it can't be racemic, right? It can't be a chiral center. Well, it is a chiral molecule because this carbon is attached to this carbon, but that carbon is attached to 2 H's and a C, where this carbon is a doubly bonded to an oxygen and another C. So this carbon is different than that carbon. Well, what about this carbon over here? Well, this carbon is actually, well, it's not attached to a carbon at all. That's a nitrogen. So nitrogen, hydrogen, but the 2 carbons it's attached to are attached to different things down the line. So again, you can't just look at what it's immediately attached to. You have to keep going to see if there are any changes further on in the molecule. It could be 10 carbons away, but if it's different, that thing's chiral, period. It will fit into things differently because of that chiral nature. Literally, it won't fit into an enzyme because it's a mirror image of the thing that it's trying to react with instead of the correct image. You cannot put your right hand in your left glove kind of situation. Right foot does not fit in your left shoe unless you're like 1. Yeah, the L version of glucose it's not problematic in any way. It's just useless. You pee it out. And the interesting thing, it's got no taste. So for a long time, people have been trying to use, to get rid of it, trying to figure out a way to make one of these things that we can't metabolize, but also is sugary in its taste. So non-caloric sweeteners. Hey, Mary, I'm in class. I'll call you back. Okay, let's see. All right, that's so we'll talk a little bit about some reactions. So we've got alkanes. They're kind of useless other than for combustion reactions. We can do a little bit of halogenation of them. We need UV light to do that. The UV light breaks the bonds for the halogen. And so now I've got like a bromine or an iodine floating around the solution. So it's powerful enough to knock the bleach off and you can get an alkyl halide. And then the last one is you can deprotonate or dehydrogenate them by using platinum at the correct temperature and pressure. And that way you can make double bonded molecules. So instead of having propane, which is really not super useful, you can end up with propene, which is ridiculously useful. The alkenes are way more reactive. And so we've got a dehydration reaction. And this is probably, I don't know, maybe 80% of all chemical reactions that happen start with this process because ethanol is so easy to make. Ferment corn, pull ethanol out, then do a dehydration reaction to get ethene. And now I've got a carbon with the double bond on it. That thing is used to make, you know, I don't know how many things in this room. All of these plastics in this room, the carpet, the tables, the chair backs, the chair bottoms, the garbage can, the plastic liner of the garbage can. Like all of these things, the wristband for my watch, they all started with an alcohol that was formed from most likely corn that was dehydrated into ethene. And then they propagated many reactions to get whatever it was that they were looking for. So possibly the most important reaction because it's where everything starts. It's like making the Lego. I make the plastic, which is in this case the alcohol, and then I make a Lego out of it. And now I can build whatever I want because of that double bond. You can do addition reactions with the double bond. You can like throw in some H's and you can go right back to propane. This seems kind of dumb, but in this case, this is what people were doing to make corn oil into animal fat, right? They were trying to get this double bond in the corn oil in the oleic acid to go away and just be all single bond so they can make stearic acid. So we definitely do that. We're better at it than we used to be. You could put a double bond around it. So this is what we were talking about at the beginning during the homework, Grayson. That double bond, those two I's on that pentane molecule and the two C's on the cyclic propane molecule. It was probably a double bond like this. You added the chlorine or the iodine, it breaks the double bonds and one of each of them goes across that. I can make an alcohol pretty easy if I've got something that's got a double bond. If I got a double bond, I can just throw in some water and heat it a little bit with a little bit of acid, and then I end up with an alcohol. Probably not common because the alkene is usually more important than the alcohol, but I can go that direction. And then I can just put one halogen on instead of me using the actual element. I just go with the acid version. So hydrobromic acid is going to put a Br and an H on, crossing that double bond. And the interesting thing about this molecule is you have two options with this, right? When the double bond breaks, the HBr could send the H to the carbon number 2 or carbon number 1. And so what happens 95% of the time is the H goes to the N. And then the other thing goes to probably position number 2. And that's about electron stability, not something that we're going to talk about in this class, but that's why in the molecule before, it's isopropyl alcohol that got formed, the alcohol group being in the central carbon instead of being on the N carbon. Because the H, the easiest way to think about it is the H always goes to the carbon with more H on it. And then the other one goes to the other carbon that's got a slot that needs to be filled. So I break that double bond. Carbon 1 and 2 both need something. The H goes to the carbon with more H, and then the other thing goes to the other carbon. So that's what we end up with these molecules. So this can be, again, I talked about this being problematic. If I wanted that OH to be on the end, if I wanted to make one propanol, only 5 or 10% of what I make is one propanol. The other 95% is isopropyl alcohol. So I'm going to have to do like a fractional distillation to separate the two out. And it's going to be kind of a pain to actually do that. But if that's what I need, then so isopropyl alcohol is really cheap, and one propyl alcohol is about 100 times more expensive just because it's harder to get. That's it. That's all we got for this class. So